Okay, so you have had a good dose of mathematics, I guess. Enough or not enough? Enough. That is only the starting. Maja aaya nahi abhi tak. But anyway, we won't go beyond this. So, that is the basics required. Transformations is required. Okay, in robotics, if you don't know transformations, then there is no point. So, just basic forward kinematics, inverse kinematics is required. Okay, we change topic now and move on little bit to sensors, actuators, then we will look at valve programming. Okay. So, sensors, actuators to be followed little bit by valve programming. So, the basic subsystems in a control system or a control module of a robot is the controller, so which is here. So, we talked about this in the morning also, that the controller is essentially electrical. It can be PC based, it can be DSP, it can be microprocessor. Nowadays, there are a lot of very cheap controllers like the Arduino and the PIC controllers. They are very cheap and they are very good. Yeah. And that is also the effect of the size effect. You know, the size effect is the cost. Electronics is becoming smaller and it's become cheaper and it's becoming faster. And it's not possible to believe that 10 years ago, I mean, you have a controller like Arduino, you know, which can control at such a high frequency, and you can take sensor input, output, do all kinds. You can literally run a robot using that. Okay, and it costs how much? 600, 700 rupees. So, so we have a controller, then there is an actuator, which is a sensor, actuator. Then we have the actual robotic mechanism, which are the links. Then we have some kind of feedback device, and the feedback device goes to the controller. So, this is the basic control structure. So, it essentially consists of controller, actuator, sensor, process model, and the robot itself. Okay, so, these are 4 different units. Now, in this unit, we have the actuator here, which is going to give motion to the motion device here, either a link or a work table in the case of an NC machine, and an optical encoder for feedback. Okay. Now, if you are going to define each one of them, first of all, why is there a controller and why is there a feedback like this? Okay. So, this is the feedback, general structure of feedback control. So, if you look here, the controller is essentially electrical, and what kind of electrical is digital electrical. Okay, it does not understand analog also. So, this is a digital device. Okay. Now, the motor is an analog device. Okay. It does not understand digital, although we are controlling it using PWM, which is digital. Okay. But essentially, this is an analog device. This fellow moves here, and then when this moves, we need some kind of feedback, which is the feedback sensor. So, there has to be something back here which is coming in here. Okay. So, now if you look at this essential components of here, actuator and a sensor. So, we require an actuator and we require a sensor in a system. Okay. So, now if we talk about definitions, how would you define an actuator or how would you define a sensor? If somebody asked you that you are talking of actuators, but what is an actuator? We are talking of sensors, what is a sensor? So, what is an actuator? I am sure you would have used the term sometime. You also would have used the term sensors. So, what is an actuator? It signals is given from here. Controller is the one that is giving the signal. So, what is an actuator? A general definition, because we have all kinds of actuators these days. We have smart actuators, then we have DC motors, which are conventional actuators, then we have nano actuators, we have molecular motors, and they all work differently. So, what is an actuator?
Which gives the force for the actuation to the any link or mechanism.
A little bit more general definition. It converts. Is it always electrical to mechanical?
That is part of the transducer. Conversion is part of transducer.
Transducer is a sensor.
Sensor and transducers are.
So, actuator is something different, yeah. Sensor is something different.
And transducer is in between.
No, it is not in between. Sensor, transducer is a part of a sensor. We will come to this. Okay. So, essentially, this is an actuator, this is a sensor. So, an actuator, what is the definition? The definition of an actuator. So, actuator essentially converts energy from one form to another. It can be electrical, it can be thermal, it can be chemical, it can be any form of energy, but essentially it is converting energy from one form to another. In this case, it is converting electrical energy to mechanical energy. Why? Because this is mechanical motion. So, it is mechanical energy. So, electrical energy to mechanical energy, it converts, an actuator converts energy from one form to another. then what is a sensor?
This senses any physical parameter which is to be measured. Physical parameter may be the temperature, maybe the pressure, maybe the electricity, maybe the photosensitivity, any kind of the physical parameter.
That one that is actually doing that is the transducer.
No, transducer is it senses and then it converts into the electrical signal. Like the pressure is being sensed by sensor and it is converted into the electrical form of the signal. Then that is a transducer.
So how would you actually define a sensor?
Sensor senses the input condition in the same form.
A general definition. It should cover everything. A sensor also converts energy from one form to another.
The quantity is intended to sense that will,
A sensor also converts energy.
but in the same form.
No, no,
Thermometer
no. So sensor also converts energy from one form to another. Here it is converting electrical to mechanical. This fellow is converting mechanical to electrical. So a sensor is inverse of an actuator, isn't it? What the actuator does, the sensor just inverts it. Why? Because this fellow can understand only electrical signals. So what is going out here is electrical. What is coming back here also has to be electrical. But what is the motion here is mechanical. So it's electrical, mechanical, mechanical, back electrical, and then back there. That is our feedback control loop, right? So say an actuator essentially converts energy from one form to another, and a sensor also converts energy from one form to another. Normally, whatever the actuator is doing, the sensor is reversing it. Why? Because here, if it is measuring position, it has to convert it into electrical, then only it can come here. Otherwise, this fellow will not understand. Okay? So there are many examples. So we will see some of them as we go along. So this is the essential feedback loop, which is electrical. So we have an electrical controller, which is giving output electrical signal. The actuator is converting it into mechanical signal. The sensor is reading the mechanical signal, converting it back into electrical signal, and giving it back there. Okay, that's the whole definition. And we can change this in different ways. So different kind of actuators, different sensors, but the definitions are the same. Okay, so there are essentially four sensors, actuators, controllers, and system model. And we have two kinds of control loops. One is an open loop, another is a closed loop. So in open loop control, there is no feedback. Okay, and obviously this is much cheaper because there is no feedback. Okay, so industries which are not interested in very accurate control, they still use open loop control. This is closed loop control. When you use very accurate control, then you need to use a feedback control. Okay. Now the general classification of sensors are divided into two classes. One is internal sensor, that is required for the basic working of the system, and there are external sensors which are required for interaction with the environment. So internal sensors are required for the basic working of the system, without which the system cannot function. Say for example, in a robotic arm, we will be having sensors and actuators at different points. Okay. So the way the structure is put is that every joint will have one motor, one gear, and one encoder. Okay, so each of them will have one unit of this, and this basic structure is called independent joint control. So all the joints are controlled independently. So each of them will have one motor, normally a DC motor, AC motor. There will be a gear in front, and there will be a position encoder or a position sensor at the back side. Okay, and if any of the sensors go bad, for example, if the encoder is gone there, then the system is finished. The controller cannot work anymore. Okay, so internal sensors are the ones that are required for basic working of the system. For example, position sensor, velocity sensor, acceleration sensor, because the feedback will normally have a position loop, it will have a velocity loop, it will also have an acceleration loop. Okay, so you need all these three to control it accurately. And external sensors are the ones that are required for interaction with the environment, like vision, force, pressure, etc., etc. So in the human body also, our sensory system is divided into internal sensors and external sensors. So internal sensors are the one without which the basic system will not work anymore. So can you name a few of them?
Blood pressure, heartbeat.
Yeah, heartbeat, blood pressure, temperature. So without that is the basic working of the system. Okay, we cannot control anything of that. That is the internal structure. So those are internal sensors. Okay, they control the basic working of the system. So similarly, in a robot, it will be velocity, position, acceleration. What about external sensors? Vision, hearing, interaction with the environment, right? So essentially, eyes. How many are there? Five. Some even claim to have 6. Okay. So but essentially it is 5. So, vision, touch, hearing, smell and taste, right. So, we have 5 sensors classified as external sensors. So, in the robot also we would be having internal sensors and external sensors. Okay. Now, the different kinds of internal sensors that are there are essentially position, velocity, acceleration, and there are different kinds, for example, potentiometers, encoders, LVDT, tachometers, accelerometers. These are essentially used for sensing the position, okay, in the closed loop control. So, very briefly we will go through some of them. You might have studied this earlier, but as we progress towards control you will be requiring that. So, I will just go through for the benefit of people who have never gone through this. So, essentially potentiometer working is very simple. So, there is a wiper which is basically a resistance coil, and there is a wiper which moves on the resistance coil. Okay. So, this potentiometer, if it is fixed onto that joint there on the robot arm, then the joint would be fitted onto the wiper, and when the wiper moves, what will happen, the ratio of the small r to the capital R will change, because the wiper is moving. Okay. So, we can calibrate it by saying that this is 0 and that is 180, and have some kind of a calibration chart which shows that for whatever is the ratio r by r, what is the exact position of that wiper. So, this is the rotating type of potentiometer, this is the linear type of potentiometer, both of them work, and this is the solid state one where there is a thin film resistor. Working principle is same, there is a wiper and this moves on that thin film resistor. So, essentially it works with a ratio of small r to capital R. Now, this is very cheap, okay, it costs 100 rupees, 150 rupees. It is not bad, you can get accuracies of 0.5 degree. Okay. So, it is not bad, 1 degree, 1.5 degree, it is okay, but it has effects. The effect is that it has some kind of bad effects. One of the bad effects is that because this is actually in contact there, what will happen after some time, this will start rubbing with that, and this contact will wear off, because there is physical contact between the two. The second is that because there is rubbing in there, in terms of the signal, there is a lot of noise in the signal, because something is physically moving. Okay. So, there is noise in the signal. The third is because it is resistance, it is affected by temperature. Okay. So, with the change in temperature, what will happen, your R by R ratio will start changing. Okay. So, it is not very accurate in that sense, okay, but it is good enough for very crude applications. Industries still use this, where you are using indexing, for example. Okay. You want to go pick up part from here, put it there, where your accuracy is not less than say 1 millimeter or 1 degree. In that case, this is fine. The other one which is used more frequently is the incremental encoder. Okay. So, the incremental encoder is the sensor that is used extensively, okay, on all position measuring devices, and lot of this, like I was saying in the morning, that you might think that robotics is far away from your life. Sensors, actuators, controllers have nothing to do with your life, but it is not like that. Okay. All the sensors, actuators are everywhere, you would have used them somewhere, okay, even for things like shopping. Okay. So, you have used an encoder, okay, definitely somewhere it is there. Now, how does this work? So, essentially it is a ring which has this slots cut in. So, how it works is there is a photo emitter and a photo receiver on the other side. Okay. So, when photo emitter is just an IR or a photo emitting diode, and the photo cell is the photo receiver. So, when the light goes through, it will give a voltage, and when no light is going through, it will give 0. So, it gives a 0 and a 1 signal. So, which is something like a 0 and a 1 signal. So, essentially it will give 0 1 0 1 0 1 0 1 in that order, that binary sequence. Okay. Now, nowadays we have the computer mouse which has an IR below, normally has a camera, but in the couple of years earlier we used to get a mouse which used to have a ball inside. I am not sure if you have noticed that. So, there used to be a ball which has, if you open the rear side, so there was a ball at the back side and there was rollers. I do not know how many of you have opened a mouse. Opened a mouse means computer mouse, not the real mouse. So, there was a ball and a roller. So, here if you notice very carefully, there would be one encoder here and another encoder here. So, there would be an emitter here and a receiver here. Okay. Similarly, there will be an emitter here and a receiver here. Okay. So, the light will go through whenever the transparent part comes in, you will get a signal of 1, whenever light does not go through, you will get 0. So, your basic sequence of signals is 1 0 1 0 1 0. So, binary signal you will be getting, right. And now, with this signal, because it is binary, there is no need for signal processing. The controller can actually understand this, because it is a binary signal, right. So, it is just a high low high low. Now, how would you figure out what is velocity here? This is telling position. So, suppose this is 360 degrees for one rotation and there are 200 slots cut, then what is the distance between each of these two? 360 by 200, okay, it is 1.8, right, degrees, right. That means the spacing between each of this 0 and 1 is 1.8 degrees. So, if it is 1 and the next you get 0, that means it is 1 point, it has moved by 1.8, right. Now, how can we find velocity from here?
Successive rotation difference.
I know the distance. So, if I know the time, say del t, okay, then del theta by del t is the velocity, right. If I know this many bits has gone through and it has gone through in say 2 seconds, then I know what is the distance it has moved and how much time 2 seconds, then I know what is the angular velocity incrementally, incremental velocity, right. How can I find acceleration from here? So, the difference between these two minus theta 2 by del t again is acceleration. That means, from one signal, very simple thing like an encoder signal, we can get the velocity, we can also get the acceleration, right. So, from an encoder we can get acceleration, we can get velocity and we can get position, and these three are required in our closed loop feedback control, okay, for controlling the joint. And so, the basic signal that comes out is something like this, and high low kind of a signal, right. Now, in this mouse, if I move this side, this fellow rotates, if I move this side, this rotates, and if I move in cross direction, then both of them rotate. That is how the mouse in the computer works, okay. If you move it, it moves in direction. How does it sense direction? How does it know whether it is going this side or is going this side? Because the signal will be the same. It is only 1010, isn't it? So, if it is moving this side or is moving this side, the signal will be the same. Then how does it know which direction the mouse is going? When you are moving, the arrow also follows your direction. How does it know the direction? So, what is done is, there are two of these fellows sitting with a slight offset, okay. So, between these two there is a small phase shift, okay. So, depending on the leading and the lagging of the two signals, it can figure out which side it is going, okay. So, if you look very close, it is very small, so you cannot see, the actual device is really small, okay, but there are two of them there, and both of them have some phase shift such that it can figure out from the phase shift, it can figure out which side it is going. So, the mouse can actually figure out whether you are going this side or you are going that side, okay. Now, this is extremely very cheap device. It costs how much? It costs nothing, next to nothing, because your mouse costs 100 rupees these days. So, if this thing was costing anything, then your mouse would not be 100 rupees. The actual price of making the mouse is probably 5 rupees or 10 rupees, and then it comes from China all the way. That is where the cost is. So, the actual cost, because this is just plastic with cuts, that is it, it probably costs nothing, okay. And because of which, in 99% of positioning measuring devices, an encoder is used, okay, because it is very accurate, it gives a binary signal, the controller can straight understand, and it costs nothing, okay. Now, the only problem with this is, it has a resolution of 1.8 degrees. So, 1.8 degrees is not great, it is very poor actually, okay. So, what is done is, one encoder is not used, two encoders are used in parallel. So, we have one encoder here. So, we have two encoders sitting in parallel. So, if this is one and this is the axis, there is another one behind it. So, if the cuts are like this, okay, if this is the axis of rotation, okay, then another fellow will be sitting with, which is with a slight phase shift. If you can understand what I am trying to say, is there is one here, okay, there is one here. So, they will sit in parallel like this with some phase shift, okay. So, that when you see from here, it will have some phase shift now, okay. Now, what happens in the phase shift is, if you see this is encoder A and encoder B, because there is some phase shift, this fellow signal and this fellow signal, there will be some lag, there will be some lag between the two signals, because they are phase shifted, right. Now, if we use an XOR gate, the logic gate XOR, so A XOR B, the XOR gate logic is that if there is any change on any signal A or B, then there will be a corresponding change in the signal here, that is the XOR gate, right. So, if you take both of these signals and XOR pass it through the XOR gate, then any change here, say for example, it is 0 0, it is 0, here there is a change in signal, it is becoming 1. So, there will be a corresponding change here, then again it is constant, okay, it is constant here, then suddenly there is a change in signal B. So, there will be a change here. So, any change here or here will have a corresponding change there. Okay. So, if you XOR this and that, what we get is we see the resolution has gone up. Okay. Here you are getting only one signal, here you are getting two signals now. Okay. So, if I have three of them, then your signal your resolution will go up even more. Okay. So, normally in DC motors or AC motors or position control devices, one encoder is not used, but there are two encoders which are used in parallel. Okay. And then the electronics, what we do is we do the XOR signal between the signals and then convert it such that your resolution has gone up. Okay. And this is the one that is used, it is very cheap, the electronics is very easy, that is why it is used extensively, okay, in AC motors, DC motors, anywhere. Now, the disadvantage, not the disadvantage of this is that we have, it is an incremental device, that means there is no absolute here, okay, it is incremental. So, there are other kinds of encoders which are called absolute encoders. Now, absolute encoders working principle is exactly same. So, we have this, in the previous case we had only one row, now we have four rows, one here, one here, one here, one here, four rings. In the previous case we had one ring, it is almost similar working, but now with four rings. Now, each of the rings has either a opaque part or is a translucent part. Okay. So, this fellow could be the let us call this the opaque part, no light goes through here, light goes through here only. Okay. So, here what is happening is, if no light is going through, then it is 0 0 0 0, if light is going through there, then it is 1 0 0 0. Okay. So, we can form the corresponding code and each of these sectors are unique, you can see here. Okay. So, each of the sectors being unique, whatever is the output there, you can actually correlate to which sector it came from. Okay. So, this is an absolute device which actually tells you that where is the exact location of that sector also, which is not possible in the incremental encoder. Okay. Now, this one basically works on the gray code, not on the binary code. Okay. And the coding that is followed here is essentially gray coding, okay, not binary coding, and this is used in NC machines, okay, then other position measuring devices, but this is rarely used because it is expensive, you need electronics with this. Okay. So, 99.9% of cases that is the one that is used. Okay.
So, in gray coding, like there is only one bit change,
yeah,
but in this picture, like
this one is binary.
Yeah, this is fine. Oh, so the actual one is
actual one is gray. So, in binary coding and gray coding, the difference being in binary code, if you are going from one number to the other number, the change in the number of bits is not constant. Okay. Sometimes you will have one change, sometimes you will have two changes. Now, that is a problem for the machine. Okay. So, they normally use gray code such that the change in gray code the change is only one unit. Okay. That is the difference between gray and binary. Now, acceleration and velocity sensors, we can also find acceleration and velocity from these position sensors like incremental encoders, okay, that we have seen. Now, you can also find velocity and acceleration from sensors like a DC motor. So, DC motor can be used as an actuator, it can be used as a sensor. How as a sensor? Now, you know the working of a DC motor is very simple in the sense that we give a voltage and it generates an electromagnetic field, okay, magnetic field. Now, because there is a magnetic field here, this field will interact with that field and it will cause a moment, okay, because of which it rotates. Now, if you see the reverse, that if I rotate this, then because this is a moving conductor in an electrical field, in a magnetic field, there will be EMF induced in it. Okay. So, if I have some kind of calibration between the voltage that is generated in there and the speed at which I am rotating, then I can have a straight line and draw a graph. Then for any voltage, I know what is the corresponding speed. Now, that is essentially what we call a tachometer. So, a tachometer is essentially a DC motor, and how it works is essentially it picks up it converts the voltage, the rotating speed into a electrical voltage, and by measuring the voltage you can say what is the speed. The other sensors are on off sensors. So, these are external sensors. So, internal sensors are essentially position, velocity, acceleration. External sensors are on off switches, emitter receiver pairs, thermal pressure sensors, force torque sensors, etc., etc. So, proximity sensors are essentially for checking the nearness to an object. For example, if a mobile robot is moving or you have a robot in an industry which is picking up a part. So, we must know when the part has come, the robot must be informed that the part has come. So, there has to be some sensor which is checking it. Okay. So, such sensors are called proximity sensors or inductive sensors. So, these are proximity means they do not touch. Okay, these are not touch sensors. Touch sensors are physical contact. These ones do not have physical contact, they just work on proximity. How it works? Working is simple. We have a north and south pole magnet here, and there is a coil. There is a copper coil. Sorry, there is the coil. These coils are wrapped onto a cylinder. Okay, so this is a north south permanent magnet, and there is maybe a plastic cylinder in there, and on top of that, these copper coils are wound. Okay. So what happens here is, under normal condition, the lines of force move like this. Okay, and the lines of force do not cut the coils there. But the moment something comes in front, for example, a ferromagnetic material has come in front, what will happen? The lines of force will be pulled out. Because of induction, what will happen? The lines of force will be pulled out and it will go through this steel or iron body now. Now, from here to here, you see that the lines of force have actually cut the coils and then become like this. So, the moment the lines of force cross the coil, an EMF will be generated. So, it is something like a on off kind of sensor. Okay. The moment something comes in front, there will be a small voltage generated, and then you understand that okay, something has come in front. The disadvantage being that this is working only with ferromagnetic materials. For the industry, it is okay, because in the industry normally they deal with magnetic material only. And mainly it is mild steel or something like that. Okay. So, for the industry, they use this inductive sensors for checking if there is something in front. Okay. The second kind of inductive or proximity sensor is the Hall effect sensor, and the working of the Hall effect sensor is also very simple. So, we have a horseshoe magnet like this, north and south. Now, the Hall effect sensor essentially checks the presence or absence of magnetic lines of force. Okay. So, if there is a magnetic lines of force passing like this, okay, the Hall effect sensor understands that the magnetic lines of force are passing through. Now, the moment something comes in front, an object comes in front, the magnetic lines of force will be pulled out like that. Okay. So, from here to here we see the magnetic lines of force are moved out. Now, the moment it moves out, there is no line passing through this now. Okay. Now, it understands that something has come in front. So, the lines of force has moved out, right. This sensor has is very small, very cheap. Okay. It is a MEMS sensor, so it is very small. It is about 3 millimeters or something. Okay. And the working principle is very simple. Electronics is very simple. It is very rugged. It is solid state. There is nothing moving inside. Okay. So, it is very rugged. Okay. And it is extensively used. Where?
Mobile. It is also used in the mobile phone covers. Like when you open the cover, the mobile phone switches on, like the screen, like they use all this.
The Hall effect is inside. On the cover, there is a magnetic.
Yeah, magnetic.
Yeah.
The sensor is
But everybody's mobile phone does not have that, I think. But something that you have used, automobile. Everybody has gone on a car, I believe, or a bus. How do you sense the speed of a car? So, when you travel in the car, the speedometer shows you the speed of the car. How is it showing the speed of the car? How is it sensing? So, sensors, actuators are everywhere, right. Something is moving, there is a sensor, actuator somewhere. Something is being picked up from somewhere, there is a sensor. So, how is the speed of a car measured?
By tracking the rotation part, I guess, and the Hall effect sensor picks up the rotations.
So, there is a Hall effect sensor. There is a Hall effect sensor. Where?
In the
Wheel. Not in the wheel. So, if you open the wheel, will you see any sensor anywhere? So, it is not in the wheel. Under the meter. It is not near the wheel.
maybe where the axle is joined to the motor.
No, maybe here, maybe there. So, normally just when the shaft comes out of the gearbox, there is a small projection on the shaft, and there is a Hall effect sensor there, which is exactly working in the similar way. So, this is the projection on the shaft. So, when the shaft is rotating, this fellow picks up the signal. How many times the shaft is rotated? That will tell you what is the speed of the car. Okay. So, a Hall effect sensor is extensively used. It is very rugged. That is why it is put in cars, and cars in Indian roads, you can imagine what kind of life it has. Okay. So, it is solid state. So, it does not break with anything. There is no moving part. Okay. it does not require any excessive power also. Okay. So, Hall effect sensor is extensively used for checking for cars speed, then for navigation of mobile robots, picking up speed for this kind of applications, then proximity. Okay. This is extensively used. It is not very expensive, hardly about 250 rupees. Okay. The other kind of sensors which are used extensively are ultrasonic sensors. Okay. And the working of ultrasonic sensor is also very, very simple. The working is essentially based on the ceramic transducer or a piezo crystal, which is basically piezo. So, if you give it a charge, what will the piezo transducer do? So, piezo crystal, if you give it a charge, it will expand, right? It will create a pressure. So, if you give it a pressure, it will create a charge. So, it works both ways. So, what is done here is that a charge is given to this crystal at a particular frequency. Okay. So, every time you give it a charge, what will happen is it will expand. So, if it expands, means it will create a pressure wave this side. Okay. So, it is being actuated. So, these are the actuations which are going on at that frequency, and it is creating that wave which is going out, which is in the ultrasonic frequency. Okay. So, it is an ultrasonic wave which is going out from here. It will hit the object and then it will come back. So, if it comes back, it is going to hit this crystal again. So, it is a wave coming back now. So, once the wave hits this, it is like a small pressure wave. So, that creates a charge. So, this is the outgoing signal, this is the signal has gone out, this is the signal that has come back. Okay. It has got attenuated because it has gone off far and come back. So, the distance between this will tell you how far the signal has gone, because you know the speed of sound. And then when it has come back, the time that it between this signal and that signal essentially tells us how far it has gone and come back. Okay. So, these sensors are very cheap, 150 200 rupees. Okay. And why I keep saying very cheap is that in engineering colleges and students, they can use this extensively. Even here they can make all kinds of real good robots by using very cheap sensors, controllers, actuators. Okay. It is not that robotics, to make a robot you need a lot of money and do, those days are gone. Okay. Today you can make one good robot at very, very low cost. So, this is an ultrasonic sensor which is used extensively in mobile robotics, for example, in obstacle avoidance. So, they would not put one of them, but they would put a ring of ultrasonic sensors around. Okay. So, when it is moving, some of the sensors will pick up the signal. Okay. Now, apart from this, where is this used? Again, you might have seen or you might have used also. Car parking. So, in the back of the car, a lot of these cars have the sensors which can sense if there is something behind, and then it displays on the front. Okay. The small round you will find the back of the cars. So, that also is an ultrasonic sensor, right. The working principle is exactly same. Now, the working principle is same. In the lab, we also have experiments with this. So, you will actually see how to take signals and then what you can do with this, how mobile robot actually works. But very often this gentleman does not see. Okay. That is why it is very bad. Why it will not see? Say, for example, if I have a mobile robot and I put one sensor in front and I leave it on this floor, there is very high chance that it will not see this. It will not see this chair's legs, and it will go and hit there. That means it does not see. So, why is it so bad that it cannot see? Or if I reverse the question, what kind of objects it will not see? Huh? Narrow means what? Rounded object. Why? So,
sometimes waves are absorbed.
yes. So, if the ray goes out like this, if it hits normal to the surface, only then it will come back here. If it does not hit normal to a surface, it will go off somewhere else. So, cylindrical objects, then a spherical object, it will not see. The other thing is it may get absorbed. So, like if you are standing, a human being is standing, if you see the legs, our pants will absorb, cloth absorbs. So, if somebody is standing, very often it will not see. So, they do not put one sensor, they put say maybe 15, 16 sensors, then they will average all the readings. So, maybe if 3, 4 are not seeing, the other fellows will probably see. So, that is called sensor fusion, or they will use different kind of sensors, ultrasonic with laser with vision, and then fuse it. Okay. So, normally we do not use one sensor, we use multiple sensors. But it is interesting also that this fellow which is very cheap, okay, and can be used for simple mobile robot applications, can be used for avoiding obstacles in by a robot arm. Okay. It can also check for presence or absence of somebody going through the door. Okay. But its implications are very, very large. Okay. What are the implications? So, if you do not want to be seen, now you know what to do, because this cannot see certain things. So, if you do not want to be seen, then you know what to do, and that has very, very large implications. Why? Because in the airports and all, you see the radars working. The radar is an ultrasonic sensor. Radar working principle is it goes round, it keeps giving out these ultrasonic rays, and then it comes back and it receives the rays, right. So, a working of a radar is essentially working of this only. So, if you do not want to be seen, now you know what to do. So, all these aircrafts and ships these days, the stealth. So, the shape should be such that the wave will never come back, it will go in some other direction. So, the CAD profile is such. Then they use paint which is absorbing, it absorbs it, and they use coating of materials on top again which absorbs it. So, very small thing, 150 rupees, the effect is where, right. It is a $1 billion industry, how to make stealth fighters, and only few countries in the world have it. Okay. So, very small thing like this, and where are the implications? But it is interesting that we use it extensively, but we use a lot of them together and then we fuse normally. But you should be aware that very often it will not see. The next kind of sensors are touch sensors, okay, pressure sensors. So, touch sensor is essentially the computer keyboard and the other kind of sensors that work on touch. So, essentially we have a conducting layer on top and PVDF layer on here. So, essentially there is a circuit layer here, printed circuit board, and there is a layer on top. So, when you press, what it happens, it shorts it there basically. So, in the keyboard of the computer, for example, if you press a letter, it shorts that, okay, and then you know where it is. Pressure sensors work exactly the same way. Okay. So, how pressure sensors work is essentially we have different electrodes. So, these are the electrodes, and there is a layer of conducting rubber in there. Okay. So, in the normal condition, charge will not flow through this, because there is an air gap which is an insulator. So, what would happen is if I press it here, say for example, here by putting our fingers we are pressing it, then what is happening is some of the rubber is getting in there. So, if the rubber gets in here, it will short. So, some charge will flow from here to here. Okay. Now, the charge is proportional to the amount of rubber which has got in there, which is proportional to the pressure. Okay. So, indirectly we are measuring pressure. Okay. So, these are pressure sensors which are used for measuring pressure, application of pressure. Now, the other sensors which are there are force sensors, okay, for measuring force. Okay. So, force sensors are a little complex in the sense that can you measure force? Can you measure force? Can you measure force? What do you think? Suppose I say at this point in space, how much is the force acting? So, at this point in space, if I say you please measure and tell me what is the force acting. So, can you measure force? You cannot measure force. You cannot measure force, okay, but you can measure the effect of force. So, you are measuring strain, you are not measuring force, because you cannot measure force, right. So, how is force measured? So, essentially we are looking at strain. So, strain has to be caused at some point by a force. So, what is done is essentially, if we have a cantilever beam, okay, so this is a cantilever beam and we apply a force here. Okay. This will cause a strain at this point. So, the beam is going to bend like that. This is exaggerated, it will not bend that much, but there will be strain here which we can measure by putting a strain gauge. Okay. So, we are not measuring force, we are measuring the effect of force there and then correlating this to that and saying that is the force. Okay. There is no way you can measure force straight. Okay. So, now one of these beams can measure how many forces? One here, 2. because there can be a strain gauge here, there will be one strain gauge here, there will be another one here, another one that side, right. So, in this rectangular beam we can measure only two forces, one acting this side, one acting this way. Okay. We can't measure any other. So, in 3-dimensional space we have how many forces and how many moments? 3 forces, 3 moments. That means, with one of this you can measure only 2, that means you need more number of them, and that explains the construction of the force torque sensor, that you have these beams basically, which is each one of them is this, and there are strain gauges which are mounted onto this end points. Okay. So, each one of them is measuring 2 forces, you can see here W1, W2, W7, W8. So, each fellow measures only 2 forces. Okay. So, we have 4 of these legs, each of this leg measures only 2 forces. Okay. And in the center of it, this is where the actual external force and torque acts. So, we will put this on the wrist of the robot manipulator, and the gripper will be fixed here, okay, on the center. So, this is the wrist, the gripper will be fitted there. So, if there is something acting on the gripper, then it will basically be acting there. So, 3 forces, 3 moments acting here will cause strains on all of these 4. So, if you can calibrate it, then we have a calibration between the external force acting and the strain. So, we can indirectly measure what is the force and the torque. Okay. Now, there is a problem there. The problem being, how do we calibrate it? So, you can start off by taking the x direction. So, this is my x, y and z, 3 directions. There are 3 forces acting, Fx, Fy, Fz, and there are 3 moments. So, moment about x, moment about y, moment about z. So, 3 forces, 3 moments, right. So, we can start calibrating by first applying forces only in the x direction. Okay. So, put some force here on the x direction, see the reaction forces. So, if you put force along this side, which two will have reaction? This fellow and that fellow. Okay. So, what I am saying is that how do we calibrate this? Okay. So, calibration basically means that I have to write my equations of equilibrium. What are the equations of equilibrium? It says the forces, the net forces in the x, y, z direction is equal to 0, and net moments in the x, y, z direction is equal to 0. So, we start off by saying that this is all 0, I am going to add Fx only. Okay. Then, if there is a force Fx along this side, then the reaction will come only on which two? It will come on this one and that one, because these are the only 2 acting on that side, right. So, in my equation of net equilibrium, I am writing Fx is equal to W3 plus W7. That is what this matrix means, right. So, this is the calibration matrix, and what it means is we are finding the equilibrium equations in the 3 directions. For forces, 3 equations, for moments, another 3 equations. Okay. And these are the strains which are acting, or the strains which are being produced on these beams, right. Okay. Now, do you see a problem? Now, we can calibrate it. How do we calibrate? We shall apply forces in the x direction, then in the y, then in the z, then mx, my, mz, and see the corresponding fellows here. Okay. Then try and find what is the gain matrix K, try and solve for this. So, what we need to find is what is the gain matrix K 1 3 K 1 7. Okay. So, once we have this equation, F is equal to gain matrix K into the W's, okay, then the system is calibrated. Okay. So, when it is going to work, if I give an unknown force, we will basically see what is the strain generated here, and then say, okay, this strain is going to cause that one. So, for which I need to invert this one. Okay. So, basically if I want to find what is W, then it must be this one is equal to the gain matrix K inverse into that. That is what it means. Do you see a problem there? Do you see a problem? There are many problems. If you look at this one, there are many problems in trying to do that.
What if you have an angled force?
If you have an angle, it will have components. It will have components. Okay. But while calibrating, we would make this. We start off with this, make all of them 0, increase the Fx force little. Then we make all the others 0, make this one, increase this one little. That is how calibration is done, right. So, finally, what we need to find is this gain matrix K. So, if I want to find this gain matrix K, there are problems. What is the problem? It is a non-square matrix. If you see, it is 1 2 3 4 5 6 7 8 1 2 3 4 5 6, it is 6 by 8. You can't invert it. Okay. You can invert it by doing pseudo inverses, okay, but then it is approximate. There is no exact inverse of this one. That is one problem. Second problem is that if you look at the Fz, where is Fz? Fz is this side. So, Fz has reactions by this one, that one and that one. There are 4 of them there. Similarly, if you look at the moment z, so moment is like this, right. So, this moment is caused by this one, and that one. 4 components are there. You might say, so what? It basically means that any combination of these 4 can cause that equivalent force. There are 4 of them now. Any linear combination of these 4 can give you the same result that side, right. Now, that is a problem, because you will not be able to differentiate your force now. Okay. So, it causes 2 problems. Number 1, it is non-square. Number 2, there is more than 2 components for a single Fz and Mz, which means that any combination of these fellows can give you an Mz. So, it is misleading. So, you could have got some Mz, you think that okay, this is my Mz, but it could have been something else. So, at an angle when it is coming, okay, it cannot resolve exactly in those directions. There will be a mistake there, because of which this force torque sensors first of all are very expensive. If any of you have used them, even very cheap force torque sensors are very, very expensive, 4 lakh, 5 lakh. Okay. Although it seems like it is what is there in there, there is nothing. 4 sticks with some strain gauges. Okay. So, essentially the real problem is here, because when you start doing the measurements or the calibration, there will be an error matrix which is coming up now, and the manufacturer has to very accurately give the error matrix. So, if you are using a sensor, you should be very careful that what the error the manufacturer has given you. Okay. So, if you are measuring a force and you are trying to measure 10 newtons and you are getting exactly 10 newtons, and you are very happy that you have got exact 10 newtons, but what could have happened, the error could have been plus minus 2 newtons this side. So, what you are measuring is probably 8 or 12, not 10. Okay. So, this you should be very, very careful, okay, because force measurement, force control is always a problem, essentially because of this. Okay. So much for force sensors and the different kind of sensors. Let us move on to actuators. Now, actuators are of electrical, pneumatic, hydraulic and advanced actuators. Okay, essentially. So, electrical actuators are stepper motors, DC servo motors, pneumatic are air pressures, hydraulic is fluid pressure, advanced actuators are ultrasonic motors, artificial muscles, molecular motors, etc., etc. Okay. Now, when would you use which one is an important question. So, if you go to industrial robots in Tata Motors or wherever, where the robot has to lift very heavy weights, for example, if it is lifting 50 kilograms, then normally the base will be hydraulic. Why? Because hydraulic gives the maximum power output. Okay. So, large robots which lift very heavy weights normally have hydraulic actuators at the base. In between they would be electrical, and the end effector would be pneumatic. Okay. So, that is the normal combination that goes on. Hydraulic is the base, electrical is in between, and pneumatic is the gripper. Okay. So, robots which require very low power, they need to lift very low weights. Okay. We can go for electrical and pneumatic, we didn't go hydraulic. So, 90% are electrical and hydraulic. Gripper is normally pneumatic. Why pneumatic? Why not electrical? So, most of the robots you will see around, they have pneumatic grippers, even in the industries. Not electrical or hydraulic. Why pneumatic? Pneumatic has some advantages. What is the advantage?
Faster response.
Pneumatic is not faster, electrical is faster. Pneumatic is safer. It is safer. So, when you have a gripper, and we said that the structure is like this, there is a motor, there is a gear in front, and there is an encoder at the back. So, when if this is a gripper finger, when this is moving, suppose it hits something, what will happen is it will not go backwards, because there is a gearbox there. You cannot drive it back. Okay. So, what will happen, either the gear will break or this part will break, because gears normally, high gear ratios are not back drivable. Okay. Whereas, if it is pneumatic, what will happen, it will just move back. So, it is safe. Okay. That is why pneumatic grippers are used for safety point of view. Suppose there is a mistake, it hits something, etc., then it will just move back, and that is it. So, different kind of actuators, again because of the size effect, what we need to look at is that there are other kinds of actuators which are also used, ultrasonic motors, artificial muscles, molecular motors, which are used at a lower scale or in special devices. So, very quickly let us go through some of the actuators. Again, you might have done this before, but we will just go through stepper motors. Okay. The working principle of stepper motor is very simple. So, we have the rotor basically has teeth, which is which is made of ferromagnetic material, and this is the so the rotor part has teeth, and this is the stator. So, the stator has windings. So, how this works? If this we actuate this winding, then what will happen? It will create a magnetic field. So, this magnetic field will induce a magnetic field here, and this is going to be attracted towards that one. Okay. So, if I switch this one on first, it will attract this, then if I switch that one, it will be pulled this side, and if I switch that one, it will be pulled that side. So, if I start switching this on in a particular sequence, I can ensure that this fellow will start moving like this. So, if I reverse the sequence, then it will go in the reverse direction. Okay. So, stepper motors are working principle is very simple. You can see this is actuated, which is here, then this one is actuated, which is here, then this one is actuated, then this one is actuated, which is here, and each time you can see the rotor has rotated. So, one this has moved in the clockwise direction. Okay. Now, so it moves by steps, and hence the name stepper motor. So, normally it is 1.8 degrees. Now, the stepper motors, because they move in steps, they can be used in open loop systems. You do not need to take feedback, because every time you are moving that much only. Okay. And if you want, so resolution is about 1.8. If you want finer resolution, how can we do that? We can actuate both of them together. Then what will happen? This fellow will come somewhere in between. Okay. So, you have got half step now. Now, if you increase the power of this, the voltage of this little bit more than this, then it will go more that side. So, you can do all kinds of micro stepping, etc., etc. Okay. So, these are very cheap. Okay. And they are pretty good. Okay. Where have you used it? I come back apparently to that question, where have you used it? Some place which is not going continuously, but is going watch is not it is piezo, no? Printer, yes, printer. Where else? Washing machine. No. The disadvantage of this fellow is it does not have high speed. It goes in the small steps. That is why in washing machine this is not used. Okay, they use DC, AC or DC there. Printer is using this. So, if you look at the printer, when it goes in small steps. Where else? Scanner. If you look at the scanner which is moving, it is not continuous motion. It moves small steps. You look at the Xerox machine. Again, there is no continuous motion. It moves little, right. So, this is extensively used because it is very cheap, it is very small, and it is pretty accurate. So, for incremental devices, it is extensively used.
How such control signals are provided, sir?
Yeah, control signals are provided in that sequence, in that particular sequence.
By means of the microcontroller.
By microcontroller. So, this experiment is there in the lab. So, whatever I have shown today, ultrasonic sensor, then stepper motor, DC motor encoder, these experiments are there in the lab. So, day after tomorrow you will actually have hands on there. Okay.
So, for this embedded kind of the programs.
Yes, yes. You can program using Arduino microcontroller. You can have even hardware based controllers, okay, that you can make on a PCB board, okay, and then do. You can also write the program in a microcontroller like an Arduino or a PIC. Both are there, both will show you. Okay. Okay, so these are stepper motors. The stepper motors can also be of linear type, where we can have a linear motor in which moves in a linear fashion. Working principle is exactly same. So, first we actuate this pole. So, this fellow is attracted, then we actuate that fellow. So, this is attracted here, then we actuate this one. So, this is attracted here, and then we actuate that one. So, what has happened? You can see that this fellow has moved in this direction. So, this is a linear motor. Okay. So, this is a linear stepper motor. No, maglev train is different. This is just a motion device. Okay. Maglev train tends to push this up also. Okay. So, here, so DC motor basically you are the working principle of DC motors you are all familiar with. So, there is no need to go into the details here. The only difference being that in a DC motor we give it a particular voltage and this fellow rotates. Okay. And in a brush DC motor there is a brush, and this is called the commutator ring. Okay. So, it is a commutator ring is there, and So, there are two kinds of brush DC motors, brush motors and brushless motors. So, what is the construction difference between them? Here the rotor has the windings, okay, and the permanent magnet is outside, and in this case the permanent magnet is inside and the windings are outside. So, the commutation has to be done electronically here. Again, they sense the direction, the position by Hall effect sensors. Normally, there will be 3 at 120 degrees, which will sense the position of the rotor, and then electronic commutation is there. Okay. The advantage being that these are much faster, and because there is no contact, life is much longer. These fellows are cheaper, but life is less. Okay. Now, cost wise, this can be 500, this can be 10,000. Okay, that much difference. Okay. So, this one which is costing 500 rupees, the equivalent one here will cost you at least 10,000 for the motor and another 20,000 for the controller. Okay. So, these are very, very expensive. Okay. Now, most industrial automation devices like robots, NC machines, they use brushless, okay, because this motor has less life because of the brush. So, all the devices in automation normally use brushless DC motors, and brushless would mean that the cost is very, very high, and that is also where the cost of the robot comes up. The link, the nuts and the bolts and the screws and the wires probably do not cost much, but essentially it is this fellow which costs, the actuators. Similarly, in NC machines also same, it is the actuator which costs, and this is an interesting note here, that there are some countries which control these motors, okay, and unfortunately India is not one of them. So, we do not have any robotics company or automation company in India, okay, we do not have, everything that we use is imported. And if we think a little bit that why is it like that, then it is not that we do not have the technology or we do not know motor control, we do not know robot control, we know, but essentially we do not have this fellow. If you buy it from outside, they will charge you 10 times, and if you put it 10 times, then you can't compete with the manufacturers. Okay. Now, if you are thinking a little bit that what is so difficult in this, what is so difficult in this, that few countries control it. So, what is difficult in this is to make this magnets, because this magnets has to be very light, but they have to be very strong. They have to be very strong. Why? Because the torque of the motor depends on the magnetic strength, directly depending on the magnetic strength. So, the magnets have to be very, very strong, and they have to be very light. Why? Because if the motor is rotating at 5000 rpm and you are trying to control it, then the inertia has to be very low. If the inertia is high, you will not be able to control at all, and that is why in terms of control these motors are very bad. You cannot control them because the rotor is very heavy. Okay. Whereas this one, the rotor is very light, you can do all kinds of fine control. Okay. And but the motors are very strong because these magnets are very, very strong, and these magnets are not the normal magnets, they have special materials and they are made in thin films. Okay. It is not a solid magnet. So, they are like strips. If you ever happen to break a DC motor, DC brushless DC, okay, then we can open it and see actually that these ones are actually fine strips, okay, and they are special materials normally made by one is niobium, the other is cadmium, okay, and that these are called rare earth magnets, and very few countries have this technology of how to make it. So, Japan is one, Switzerland is the other, Germany, US, just 4, and they control the automation market in the world. So, if you are ever wondering why the robot is coming from Japan, you know the answer, because that is coming from there. And if you want to make it, it is a good idea not to try, because the cost will never come down. If the cost does not come down, then you can't survive in the market. Okay. That is the reason we had a company like HMT, Hindustan Machine Tools, that went bankrupt because they could not make at the same cost at which you can buy a robot from outside. Okay. So, the main catch is here, and the catch here is the magnet. Okay. So, pneumatic actuators are piston cylinders, which we know, which is very, very well known. So, I will just jump it and just go to the last part, a few slides. So, in case of what we talked about, the size effect, if you are trying to make actuators which are very small, then we cannot use a DC motor because you can't make it small, after some time it will not work. Okay. Then we need to look at other devices, and these other devices are ultrasonic motors, artificial muscles, molecular motors. Okay. So, this is again something all of you have used. All of you have used. Something moves, but you can't see the motor. Mobile. Cameras, yes. So, any of the autofocus cameras where the lens moves, something is moving, but where is the actuator? If you open it or if you happen to break your camera, then please look inside closely. You will never find a DC motor sitting there. But if you look at this big SLR cameras where the lens comes off, the big lens, okay. If you see one side of the lens, it will have this one, this two-tooth structure, and on the other side you will have this one. Okay. So, when the lens is assembled, these two come together, and the working principle is very simple here. So, this is made up of a piezoelectric material, say piezo quartz or polyvinyl type of piezo material, and how it, and the rotor is in physical contact with this. Unlike a DC motor, when the rotor and the stator are not in contact, here they are in contact. Okay. And how it is actuated is that first this one is actuated, this fellow being piezo, if you give it a particular charge, what will happen? It will give a small kick in there, a small force. So, if I actuate this one, then I actuate this one, then I actuate this one. So, this will move little bit in that direction. And these are the piezo crystals which you can see, those teeth. So, at any time one of them is actuated and it moves in that frequency. Okay. So, this fellow will start rotating small. So, if you notice very carefully, when the camera lens moves, it is not continuous motion, it moves in steps. Notice carefully next time. Okay. Slowly it does, because the actuation mechanism there is this is kind of the actuation mechanism. It is an ultrasonic motor. Again, because this is piezo, it does not get affected by the size effect, right. So, you can make it very small, it will still work. Okay. And these are not very expensive, they are very strong. They are strong because there is physical contact there. So, just by rotating you can't rotate, they are pretty strong. Okay. Only by giving a particular frequency, charge at a frequency, then you can rotate this, right. So, these are very extensively used in cameras, motion devices, micro robots, micro motion devices. Even in cutting tools, in micro machines, they start using this one now, because it has very long, it is very strong, very small, but very cheap. Now, we can compare a few smart actuators. So, some of the smart actuators are called ionic polymer metal composites, which are IPMCs. The hand that I had shown, that is ionic polymer. Then we have shape memory alloys. Okay. Then we have electroactive ceramics, these are piezo basically. Now, we can look at the basic properties of some of them, for example, displacement, force generated, response time, density, driving voltage, etc., and then choose which one is it that you want. Okay. So, what is the comparison between three of them? The ionic polymers, they have very large displacement, that we have seen. They can move from one end to another end, but they cannot produce any force. If you look at the force, it is very low force. Okay. And their reaction speeds are also not very fast, and they require very low voltage, only 4 to 5 volts is required to drive them. Okay. So, if you are having an application where you require very large displacement, very low force and very low voltage, then you can use this. If you are having an application where you require very low displacement, say only 0.1 up to 0.3%, but very powerful force. So, the force is 40 here, it was only 10 there, but this operates in high voltage. Okay. Then you can go for piezo. This one comes in between. Okay. So, depending on which actuator you are using, you can use different kind of. So, some examples are given here, working of electroactive polymers. So, by giving a particular charge, what happens is the ions inside go into one side and start getting deposited there, and because of this the pressure gradient here increases, because of which it bends on that side. So, if I reverse my polarity, it will go in the other direction, and this does not have size effect. If you just cut it into small pieces, it will still work like that only, it has nothing to do with size. Okay. So, this is an example where, so this is the same one that I had used in the I had shown in the morning. So, this was made of electroactive polymer. So, these are all electroactive polymers, okay, and these come under what we call the smart actuators, smart robots. Okay. Okay. So, we will not go any further into this. This is enough for sensors and actuators. Now, before we end, we use the word smart. I am sure some of you would have used the word smart also. Smart actuator, smart sensor. So, how would you define a smart actuator or a smart sensor? What is smart? We said an actuator is one that converts energy. We said a sensor is one also that converts energy in the reverse of an actuator. But then what is a smart actuator? What is smart? We say smart material. What is smart about it?
Like which remembers its previous stage, its previous configuration, so that like the shape memory alloy.
Shape memory is an exception. It is only shape memory that remembers its shape. That is why it is called shape memory. The other ones do not. Right. So, what is smart?
So types of sensors and actuators that like work the way like we want them to, like the exact application.
A little bit, if you say that the way you want it to operate,
Like
what does that
exact
mean?
Need, like they suffice the exact need of the machine or the robot. Like.
What, say if you want to measure position, you can use an encoder.
Yeah.
That is sufficing the need, but is it smart?
Like it may be adaptive.
What do you mean by that?
Adaptive means depending upon some adverse condition, it can reflex.
So, smart essentially means an actuator or a sensor which can behave like an actuator or sensor depending on how you want it. Okay. So, smarts are those materials which can behave like actuator or sensor at the same time. They are bidirectional. Okay. Say for example, here if you are giving it a voltage, okay, it is producing motion. If I give it a motion, it will produce voltage. A piezo is in a way smart. Okay. It can do both of them depending on how you are using it. Okay. So, there are many examples of this. For example, if you are trying to do a very concrete example, if I give, say suppose this beam is vibrating, okay, and you want to measure the vibration, then I can put a ionic polymer in here. Okay. This same strip I can put it in there, and because this fellow is moving, it is vibrating, I can pick up that signal in that polymer. Okay. So, I could have put a strain gauge also, but a strain gauge is not smart. It can simply pick up the vibration and say that it is vibrating. But now, if I put an ionic polymer and suppose it is vibrating downward or it is trying to move upward, and I actuate it such that it tends to move downward, if you understand what I am trying to say. I put an ionic polymer strip here, I take this actuator, put it here. It is going to sense that this fellow is vibrating, but I actuate it such that when this fellow is going upward, this fellow will tend to push it downward, and if this fellow is moving downward, it will tend to pull it upward. So, it will cancel your vibration also. So, it can sense the vibration, it can also cancel it. Okay. So, in that sense it is smart. Okay. So, these are also called smart actuators, smart sensors, because they can do both at the same time. Okay. And applications are many, vibration control is one, then monitoring of devices is another. Okay. So, and even in micro robotics this can be used extensively. Okay. Okay. So, this much is enough, we will not go beyond this. So, in terms of the lab tomorrow, not tomorrow, day after tomorrow, we will need to do a little bit of robot programming, okay, Val 2. Okay. So, Val 2 is the language that is used extensively by all robots, and 90% robots use Val only even today. So, we will go a little bit into robot programming, but before that you can take a 5-minute break. So, a robotic system will essentially consist of a mechanical hardware, which is the arms, motion transmission, gripper. This is the mechanical hardware, right? And there will be a robot control unit, which is going to have a robot controller. It will have a robot controller. There will be motors, sensors, power amplifiers, ADCs, DSCs. So, analog to digital converters, digital to analog converters, okay, basically for communication. And then there will be a central controller for interfacing the robot with other machines. For example, a robot will not work by itself only. Okay. So, it will communicate with other machines. For example, a conveyor part is coming, or a CNC machine which is doing something, or a parts carousel where parts are coming, inspection. So, it has to interact with others also. So, there are two parts. One is the robot control unit, which actually controls the robot for moving the robot or for performing whatever task, and then the central control unit, which is for interfacing with others. So, the Val language program has both the facilities. It controls the robot, and it also does interfacing with other machines. Okay. So, we will look at the basic control paradigm, and then we will look at the So, there are two kinds of ways by which you can program. The first is a teach pendant. Okay. Now, teach pendant is something like the remote on the TV or something like this. Okay. So, it looks something like this, and there will be 1, 2, 3, 4 joint numbers. Suppose there are 6 degrees of freedom, there will be 6 joint numbers, and there will be plus minus plus minus plus minus. So, simply by pressing plus you can move the joint in one direction, or you can move it in another direction, and at every point when it is moving you can store the corresponding position of the end effector in the memory. Okay. So, you can physically move it around, store those locations, and then play back, then it plays back. Okay. So, for simple operations like pick and place, etc., you can use teach pendant. Okay. Catch it, take it somewhere, all that. But for more complex operations we have to write a program like well language. Okay. More complex operations like spot welding, etc., and these are pretty complex. For example, just to give you an example of how complex it is, if you are looking at the industrial scenario, how many of you have visited how many of you have visited any motor manufacturing company, automobile company like Tata Motors or Maruti? Or so you will find that in spot welding it is not one robot which is doing, there will be a number of robots which are working together. Okay. So, why is it complex? Because there are 4 or 5 of them and they work very fast, and they go how many spot welds per minute? It can make up to 10 to 15 spot welds per minute, that speed. Okay. So, it is working very fast, it is going into very complex places, it can go inside, it can go under the car, and there are 4 or 5 robots which are working. So, they should not also start hitting one another. Okay. So, this question of writing the program, then sequencing the operations is extremely difficult. Okay. So, there are special companies which do that, and whoever is the original manufacturer of the assembly line, they are the ones who normally do that. So, if you go to Tata Motors purchased the manufacturing plant from Nissan. It was a Nissan car company in Australia. They sold it to Tata Motors second hand, they got it cheap, so they bought it. Okay. And if you go there and see, even the programs which run there are written in Japanese, and the poor Tata fellows do not know what is going on, so they cannot change anything also. So, if anything goes wrong, they have to call those guys. Okay. They will come and change it. Okay. Because that is the way it is. So, this process is it's extremely complex, because first of all getting locations in space is not easy. We are saying get the coordinates of a point in space, which is actually very difficult, because no sensor will give you 3 coordinates. 3 coordinates plus 3 angles, 3 orientation point positions and 3 orientations, 6 coordinates, no sensor will give. So, you can't get. Okay. So, what is done is in the first, before making this assembly line, they would have a CAD model of this. Now, in the CAD model they will find out those points, okay, wherever the weld is to be done. Then that coordinates of that point will be output to the robot program. The robot program will now write the program such that these fellows go to those points, okay, and perform the weld. Okay. And then what is done is a simulation will be done, both cases simulation is done in the CAD model as well as in the robot model. Then if the simulation everything is fine, then they will come to the real world. In the real world what they will do, they will make this car body out of plastic or something like that, and then the tool of the robot also will be made with plastic or wood. Okay. Then they will run it for maybe months. Okay. They will try and see that whether there is interference between the robots, is there something going wrong somewhere, is there a damage anywhere. Okay. Why? Because suppose we have a coordinate of a point there and we are wrong by say 0.0001 millimeter, that is next to nothing, right. 0.0001 millimeter is next to nothing. But if the robot is doing 3 shifts for 1 year, it will probably do a few million cycles. So, that million into 0.0001 is a big number, right. So, even a very small number cannot be tolerated under any condition. Okay. That is why it is the companies which do this are highly specialized, okay, and they do this CAD modeling, robot safety, the programming, and that is the one that is expensive. So, the actual cost of a transfer line, the mechanical cost is 10%, just 10%. 90% is the software, safety, patent, all that is 90%. So, in an NC machine the cost is 10%, 90% is the other cost. And why? You should understand that how difficult this is actually. So, if you are trying to make a company and thinking of making a company, think twice. Okay, let us move on. So, there are 2 ways of programming, one is teach pendant, the other is program based control. See, in program based control we write the motions of the robot in a language like val, and it runs like a normal program. Now, historically speaking, there are 3 generations of languages. The first generation is for simple pick and place, okay, which is val 1. Then we have second generation, which is for interaction with the environment, which is val 2. So, val 2 basically you can interface with touch sensors, force sensors, ADCs, etc. And val 3 is val 3 hasn't come up. The third generation is what we call the intelligent languages. They are languages which should actually understand general commands. Okay. So, the person in the workshop should be able to tell the robot that assemble this part or put that nut. Okay. That is a general command. The robot should be able to understand and then convert into its own language. But we haven't got very far there, because English language can mean different things in different ways. So, the robot might end up doing something else. Okay. Like if you say tighten a nut, you do not know it is a biological nut or a mechanical nut. So, there is a lot of research here, and it is still in research. So, the first language that was made is called Victor's assembly language. It was first developed in 1960 by this company called Unimation. So, Unimation was the first company which made the Puma robot. So, the Puma robot was the first robot made 1960, primary universal machine for assembly. So, this is there in the lab. So, we will also show you the programming, val language programming of Puma. Puma is there in the lab, and this was made in 1960, and probably the name of the gentleman was Victor. That is why it is called Victor's assembly language. Okay. And we have val 1, then val 2, and 90% of the robots in the world use val programming for programming. So, if you look at a robot language, the way it is working, it will be a derivative of val. Okay. So, you can see, and hopefully after this short presentation you will be able to understand. The second language that was made was AML, and this was developed by IBM for manufacturing automation, also in 1960. Okay. And this IBM has stopped working in robotics. So, this language is gone, it is not used anymore. And there was another language called RPL, which was again 1960. Now, the structure of the language is based on the language or is similar to the Fortran language. Okay. This fellow is similar to BASIC. Okay. Those of you who would have worked on BASIC language, okay, maybe in school they still teach BASIC, because it is very basic, okay, and it is very simple. There will be one line number and there will be one line, next line number, one more line. Okay. So, it was based on this language, and hence the structure is like this only. Okay. There is one line number and then one line. Okay. It is very simple, and it is also made this way such that a person who buys a robot, okay, or a company which buys a robot, can use it easily. What I mean is, if you expect a person buying a robot to do kinematics and dynamics and control engineering and then use a robot, then nobody will buy a robot, right. So, it should be made in such a way that it should be user friendly. The person need not know anything about the robots part, the kinematics and all, just he should know some basic commands, and then okay, he can run. So, that is the objective by which it is made. So, it is very simple. So, we will be looking at val 2, which is the derivative of val. Now, the val language essentially has this 4 parts. The first part is constants, variables and data objects. Constants, you understand, is a constant. For example, pi is a constant. Suppose you are doing some calculation 2 pi r and you want pi to be a constant, then you define constant pi equal to so much, or constant name ABC equal to so much. Okay. The second is variables. Variables, they are variables which can take different values, and then there are data objects. So, this is the first part in a program. So, the program is written in this sequence. Second is motion control commands. The robot arm moves around, so there has to be motion commands. Okay. So, these are our motion control commands. Third is a robot has a hand. Now, the hand is used for picking up and for catching and picking up and placing. So, there are hand control commands. And third is program control, input output control. This is basically for interfacing with other machines. Okay. So, the robot will communicate with the NC machine or with a part conveyor, that is communication basically. So, this part of the program deals with communications with other machines. So, the first one is very simple, variables and motion command. The first is a point. The point means a point in space. This is the variable name, the syntax. Okay. So, if you say point P1, it means the name of the point is P1, and it has 6 coordinates. The first 3 coordinates are x, y, z coordinates. That means the coordinate of that point in space x, y, z, and the other 3 are the angle of the end effector at that point. Okay. So, I want this end effector to go to this point, but I am also interested in telling what angle it should go. Okay. So, I hope you understand that a point has coordinates, it has position, no orientation. A point in space has position, no orientation. So, but the orientation is also important, because the same point can have infinite orientations. Okay. So, you want a particular orientation, you have to tell what is the orientation. Okay. So, this is angle with x axis, y axis, z axis. This is the coordinate of a point 3, 4, 5. So, point P1, 3 x, y, z and 3 angles. It defines a point P1. So, we can define different points in space P1, P2, P3, P4 or whatever, A1, A2, A3, A4. Okay. Then we can move to the point by saying move P1. So, it moves to P1. The command syntax is move P1. It understands it has to move to P1. Then in terms of move, there are 2 commands, moves and moves, 2. This means moves in any way. S means move in a straight line. Why would you need 2? Okay. Or rather, if I were to come here, okay, we have a robot which is here. My point P1 is here. Okay. I say move P1, so it moves to P1. Which trajectory will it take? What is the shortest path? How do you know? So, there is one point here P1 which I have defined, okay, having these coordinates. I now say move to P1. So, it was here, it will now move to P1. Which trajectory will it take? Shortest is a very misleading term. Least time taking, least energy taking. So, when I am catching this object and I am keeping it here, okay, I am following a particular trajectory, right. Which trajectory is that? There are infinite ways of doing the task. I can come from here to here in infinite ways, but I am taking just this trajectory. So, which one am I taking? Least energy. Now, which is the least energy trajectory? So, if I asked you that you are going to control this fellow, take it from here to here with least energy. Okay. So, which one will have the least energy?
No, in which the arms will have to rotate the least, like the combined.
That is a valid question. You minimize the energy. Why? Because you want least energy anyway. So, you take it using a trajectory which has least energy. So, which is the least energy one?
Sir, the work done is F into D. F will be constant. D is the least of D.
F, your F is the torques at these joints. So, the torques are different, they are not same. Your distance, if you are talking about the Euclidean distance here, yes, that is constant, but the torques at the joints are not constant. So, when we move, least energy, how? Least joint moving? Least joint moving? So, we will move in a way that, so if we actually see when I am moving my arm, only this fellow is moving. Okay. So, here also if we say that we should go from here to here such that the least number of motors work, okay, then that gives us a solution of least energy, right. So, if it can do with moving only one actuator, only moving this fellow, so that it will go from here to here, it will do that. Okay. It saves the energy also. Okay. So, why do you need 2 then, move and moves? Sometimes you might need to move in a straight line, right. For example, when you are assembling, we saw in the case of the SCARA robot in the morning that when you are doing electronic assembly, you have to move in a straight line. Now, if you have to moving in a straight line, then you have to move straight. Okay. Now, why is this not preferred? Because to move straight means you must have infinite points on that straight line, and you have to go to those infinite points to be able to keep a straight line. So, that means excessive computation, and also sometimes it may not be possible, and excessive energy usage. Okay. So, the robot will become extremely slow, energy requirement will go up, and all kinds of things happen. So, normally we move in a straight line only when required, not otherwise. Okay. So, we can go to move is when it is just moving in space, you do not care about energy, or sorry, you don't care about straight line, and moves is when you care about straight lines, okay, when it has to go to another point in a straight line. Draw and approach are two commands which are commonly used. Draw basically means that if you are giving it a coordinate p1 and it has gone to near p1 but not exactly p1, you want to correct a little bit. Why? Because it's very difficult to get coordinates in space. So they would give an approximate coordinate somewhere near and then make a final correction. So the final correction is this draw. So this is an incremental command which says move in the x, y and z directions by that much. So this is incremental. Okay. So we can give a move command p1 and then correct it by a draw. The second is approach and depart. So approach and depart are used where you are trying to pick up an object. Okay. Now what we need to remember here is that when I am picking up an object, okay, I can see that the object is here. Okay. So I will not try to go from this side. Okay. Suppose I say p1 is here, the center of the object. I want to pick this object. Okay. Because I can see, I will not try and catch the object from this side. But a robot cannot see. Neither does it understand what is up, down, what is stable. Okay. It does not understand. So there has to be some way by which the robot should not go and hit that object. So what is done is basically we don't go straight to the object, but we go on top of the object. Okay. And that is this command which is used approach, or this is called approach p1 50. It basically means approach the point p1 and keep a distance of 50 along the z axis. Okay. So it will come on top of the object and keep a distance of 50. Okay. Then the next command can be moves, it goes down, then it catches. Now again when it goes up again, suppose I say take the bottle and keep it there, I can see that okay, there is a table here, so I shouldn't go from try and go this way. The robot may try to go inside here. Okay, it doesn't know, right? So again, for when it is going up, it should always go up, then go somewhere. Okay. So one is for picking up, for catching it, which comes from the top straight, catch it, and when it departs also it should go in straight line, then go somewhere else. Okay. So that is why these two commands are there, approach and depart. One is for going in, depart is for catching and taking out. Hmm?
Can you tell about the draw?
Draw is essentially an incremental command to make a correction. Say for example, you had given this command p1 3 4 5, and when you had written 3 4 5, this is an approximate coordinate. So if you want it to go exactly here, it has gone here, not exactly there. Now how do you correct it? So you can make a very small correction and take it there. So that small incremental correction is draw x, y and z. Okay. So basically is moves. So this can move anywhere in space. This is in a straight line. This fellow is draw, incremental command for correction of end effector. This one is approach for picking up object, depart after catching, take it somewhere.
Is there a difference in the velocity between move and approach?
Between?
Move and approach.
Yeah. So whatever velocity you have set it to, I'll come to velocity. Okay.
Sir, one thing, sir. Like when we say move from one point to other point, the robot follows the path with the least inertia.
Yes.
So where is the algorithm by means of which
Yeah.
it calculates?
So it will be there in the controller. So I think
little bit insight into that algorithm, sir, if possible.
yeah. So that I think Dr. Dasgupta considered talked about inverse kinematics, right?
Yes.
So in inverse kinematics, you can always get multiple solutions.
Yes.
So which solution are you taking? That is the mathematical question. It's a question of which solution are you taking. So here, if I say that you are moving from this point to this point in space,
Yes.
how many solutions are there? There can be very large number of solutions.
Yes, sir.
So which solution are you taking?
Like sir told in morning said 16 possible.
Yeah. So if there is 16 solutions, then out of those 16, which one will you take? So you will take the solution that will have the least number of joints moving. So the controller automatically does that. It is programmed in the controller. Okay. So it knows from the inverse kinematics there are 16 solutions. It will take the solution which has the minimum energy. Okay, and then execute. Okay. Yeah. So the next set of commands that we have are open close, open eye close eye, and close. So open eye close eye is very simple, just like English. Yeah, close the end, the gripper, or open the gripper. Now suppose we write a program something like this. suppose we give some point P1 which has been defined. Okay. So, point P1 which has been defined, then I say open, okay. Then I say move P1. I hope you understand this by now. Okay. It is so simple, there is nothing to understand. Okay. So, we have a robot here. Okay. I want to pick up this object. So, there is a robot here. Okay. So, this fellow is here and I want to pick up this object, okay. And this is my point P1. Okay. So, point P1 is taught, coordinates are given, then it says open, okay, means open is gripper, then it says move P1. So, this is my point P1. So, it moves there to P1. Then I say close, okay, and then so the gripper closes and then I say move P2, P2 is some point on top. Okay. So, you understand this, right? It's very simple. Is this correct? Is there a chance of an accident here?
Yes. First it will come to top, then it will draw, then again it will go up and then go to penalty.
Okay. So, I can
Z coordinate has to be different.
approach P1 100. Is it okay now?
Orientation of the gripper.
So now
Orientation, maybe it is a circular objects, orientation does not matter.
The force required to close and open is not
Force is normally not there, force is not required. Logically, is there a chance of a problem?
the coordinate of P1
Is already given. Say for example, I give it the coordinate of P1.
Sir, what is P1 and
So we will have to check whether the hand is open or closed before that logically.
No, see here, we are saying open, it was somewhere else, right? So, we are saying open,
Yes.
then we are saying approach P100. So, it is approaching P100. Then we are saying moves P1, it is moving to P1. Then we are saying close, then we are saying move P2, P2 is somewhere on top. So, if I logically give the sequence here, it was somewhere else, I am saying open, it is opening. Then I am saying approach P1, so this is P1, so approach from the top, it is coming there. Then I am saying moves P1, it goes down to P1. Then I am saying close, it is closing. Then I am saying moves P2, P2 is somewhere there, it is going up. What is the problem?
it's not confirm that whether that object is in that.
No, object is there and all that.
P2 is not defined?
I can define P2 by putting a point there. Okay. So, I just define. No, I am saying what is the danger here, that this logic apparently seems correct, but is wrong. So, if you think a little bit, okay, how a program executes, say it takes line by line. So, it starts with the top line. So, it will take the first line, point P1 assigned, value is assigned. Then it will take open, it will start opening. Then it takes approach P100. So, it is approaching P1 till there. Then it says moves P1, right. So, it moves down there, catches it. Then it goes to close, close, then moves P2, it goes to P2, right. That is how a program executes. But if you, the moment it says open, as far as the compiler is considered, that command statement has been executed as far as the program is considered, because it has line open, it has given the command to the gripper to open, it moves to the next line. That is how a program operates. Similarly, here moves P1, it has come to P1, then it says close, it goes to that gripper controller and says close, and then as far as it is considered, it has closed, and then it goes to the next one, says moves. So, when it is closing or it is opening, it will take some time, it is not instantaneous, right. So, when it says close and this fellow is closing, it goes to the next line and says moves, it has already moved without closing. Do you understand? Similarly, here this fellow is opening, as far as the program is considered, it has given the command to open, right, but it is taking time. So, when it is opening, in the process of opening, it is also moving. So, if the object is very near, it will go and hit the object now. Do you follow? that every line takes time, but as far as the program is considered, time is not in the picture in a program. Where is time? There is no time, right. So, in order to avoid that, what is done, the other command of open I and close I is put. So, open immediate and close immediate. Okay. If this command is given I, so open I, it will basically mean that it will monitor that that task is over, then it will go to the next line only, otherwise it will not go. Similarly, close I here, it will close and then go to the other line. Then that explains why you need open I and close I, but then why have two different commands? It could have always been open I and close I. Why do you need open and close also?
In some cases,
I hope the question is clear. Apparently, this command is enough, open I and close I, because of this danger problem. But then why do you need open and close then? Because open I and close I takes time. So, if you are not, when the robot is just moving in space and you do not care about open I and close I, then you can simply use open. So, when it is moving, it is also opening, it is fine. It is saving time. Okay. And we said that a robot will not do one operation, but it will do millions of operations. So, 0.00001 second may mean nothing, but if you multiply that into millions of cycles, it is a very big number. Okay. So, the program has to be written in such a way that the time required should be minimum for millions of cycles, and it should be safe. So, when it is moving in space and we do not care about hitting something, then open close is fine, but if it is moving to catch something, then open I and close I is used. Okay. Commands like speed is used. Okay. Speed 60 IPS means 60 inches per second. So, it can be 60 mm per second also. So, in the metric system or the British system. So, this controls the speed. So, you can control the speed by this one. Then define a path. So, path can be defined by different points, A1, A2, A3, it will follow those points. Pause, it can pause. Okay. So, after some task it can pause. Now, the simplest operation would be something like this. There is parts coming in a conveyor, we are supposed to pick up the part and keep it there. Then it takes the next one, it keeps it there. Okay. It keeps doing that. Okay. Some questions here that are interesting is, should it do the indexing by here, 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 then here, 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 then here, 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 in that, or like this, then like this, then like this, then like this, or should it do like this, like this, like this, like this, like this? Which one? Because even a very small amount of time difference will cause a time problem now. But it does not make any difference. Why? Because it always has to go to every point.
First outer boundary, then inner boundary.
It will not make any difference because it is accessing every point. So, the sigma of all the points is the same irrespective which way you went. Okay. So, normally it goes like this, like this, like this, like this. Okay. Now, if you look at this problem, there are parts coming, there has to be some sensor which is telling the robot that a part has come. So, a sensor is required, some kind of sensor. Okay. So, we looked at different kind of sensors, on-off sensors, ultrasonic sensors, inductive sensors. So, the sensor can be put here, it will take a signal that the part has come and then go to the robot and tell the robot the part has come. Okay. Now, when the part has come, the conveyor has to stop, then the robot goes and picks it up. Now, once the part is gone, again the sensor should tell the conveyor that the part is gone, please now go on. Okay. And the robot has picked up the part, put it here, now it will come back. Okay. So, this is the simplest we can have, but this does show that the machine needs to communicate with other machines, otherwise it can't work. Okay. So, what is communication between machines? This is another case where there are 3 machines and there is a robot. So, it picks up something from here, puts it here, picks up something from there, puts it there, picks up something from here, puts it there. Okay. And then something else comes, it picks up. What happens? It becomes deadlocked. Why? Because after the machines are over, somebody has to pick that up from there. Now, the robot can't pick up because it has something in its hand, right? Or in terms of cycle time, if the times are different, then it's very difficult to sequence this kind of. So, it's actually a very, very complex problem. Okay. Sequencing, when we saw spot welding, there are 5 robots which are doing 15 welds per second in all kinds of complex geometry. So, it's a very, very complex problem actually. Okay. But this does show about sensors. So, how do machines communicate? Machines communicate at the simplest level by means of on-off sensors. Now, on-off sensors are essentially on, which means 5 volts, and off means 0 volts. So, the machine, the robot controller will also have a number of channels, okay, and each of the channels will monitor whether it is plus or minus, okay, plus or 0. So, on will mean plus 5 volt, 0 will mean it is off condition, okay. And there are some logical statements like go to, go sub, return, if, then, else. These are logical statements. So, if some condition is satisfied, then do this, else wait, okay. Pause, proceed, we have seen. Now, this is the simple way of communication where the syntax is signal, this is channel number 1 0, this means plus, this means minus, this means high, that means low, okay. So, plus and minus essentially means low and high at the lowest level. So, if we say signal 2 3 or sig 2 3, then it means channel number 2 is high and channel number 3 is low, okay. So, suppose some sensor is connected to channel number 2 and connected to channel number 3. So, the robot, when it comes to this line, it will say if this signal condition is satisfied, then do this, else wait, okay. So, this is how the machines communicate with each other. So, in this kind of setup, one channel from here will be connected to this, some channel for this fellow will be connected to that, again some channel will be connected here. Those channels will be having channel numbers 1 2 3 4 5 6, and each of the channel can be low or it can be high, okay, at the lowest level. So, in this condition, for example, if we say signal 2 3, then for example, if a part has come, then your signal 2 will become high. If a part hasn't come, then it will remain low. In this case, for example, something else is being monitored. Is the machine free? If the machine is free, then it will be plus. If the machine is not free, it will be minus, okay. So, it will keep waiting for this signal condition. So, if this signal is satisfied, then it will do something, otherwise it will wait or it will do something else, okay. So, in this way different machines can communicate, okay. Say for example, in this particular case, the conveyor channel 1 can communicate with robot channel 1, okay. As soon as the part comes, it will make the channel high, okay, and the conveyor will stop, the robot will go and pick up. The moment the robot picks up, it will make that channel low. So, now the conveyor understands the part is gone, it will start again, okay. So, simply by on off kind of sensors, machines can also communicate. So, the basic syntax is signal, or sig stands for signal, 2 3 stands for channel number, plus and minus stands for high low signal, and wait signal, if it is going to wait until the signal becomes positive, okay. You can turn on a channel, you can turn off a channel, you can reset all the channels. So, when the robot starts, it resets everything and then starts from there. Now, this is for basic plus minus. There are other kind of sensors, for example, force, torque, okay, temperature, pressure. These are not on off kind, they are analog sensors. So, they give a continuous reading in terms of time. Now, a robot cannot understand analog signals, so there must be some kind of conversion which takes place, okay. So, there are analog signals which are converted to digital signals, and that is basically ADCs. So, analog to digital conversions are taking place. So, any sensor which is giving an analog signal like pressure, temperature, force, pressure, then proximity is another one, okay. It is a continuous signal with respect to time. So, it is digitized by using the analog to digital converter, and then it is given to that particular channel, okay. Similarly, if a robot wants to communicate with another device, now most of the other devices will not understand analog signals, they understand only digital signals. So, it has to convert from digital to analog, so analog to digital, and this is digital to analog, either way, okay, both ways it goes. So, if it is trying to communicate with another device, say a motor, and it wants to turn on something which needs an analog signal now. So, it will convert a digital to analog and then give it on that channel, okay. So, this is a higher level communication where it can communicate with other kind of sensors, and the basic syntax that is used here is ADC and DAC. Say for example, if I say DAC 1 is equal to sensor 1, then it will, whatever is there on DAC 1, it is going to give output to this sensor 1. The sensor 1 is just a variable name, okay, or DAC 1 is equal to constant, okay, and then DAC 1 is equal to 3 plus constant, okay. So, if we want to write a ADC number, then it is ADC 1 is equal to maybe sensor 1, then whatever is coming on sensor 1, it will become ADC 1, okay. So, it will understand that on channel number 1 there is an ADC converter, analog to digital converter, whatever sensor reading has come, it will go there and will convert it, okay. Then with that value it can do something. So, it will say that if maybe force is more than 10 Newton, do this, else wait. Okay. We have a very small example. This is a small example, but it is a complex example. Okay. If you try and write it, I am not sure you will succeed in one time. Okay. Why? Because this question of deadlock is here. Okay. The robot picks up something from here, puts it there, picks up something, puts it there. After machining is over, it picks up something, drops it there. Okay. At every time, you have to sequence the timings properly, because what can happen is, for example, if both these two parts are on the machining center, machining table, and the robot picks up something there, now it cannot take up this one and put it there. So, it is deadlocked. So, this kind of deadlock can happen in many ways, and we have to be very, very careful that it is not deadlocked. Okay. So, this example looks simple, but is not very simple. This one is a simpler example. This is a pallet which number of parts kept in there. This is the top view, okay, and we are supposed to pick up one object from here and go and drop it in that chute. Okay. So, the program is very simple: pick up one part from here, take it and drop it there. Okay. Then take the next one, pick it up, drop it there. Okay. Okay. This is a very simple problem. Okay. Now, one way of writing a program would be, a very bad way, would be pick up this part, drop there, next line pick up this part, drop there, third line pick up this part, drop there, then pick up this part, drop there, and if there are a million parts, then you do a million lines. That is a program, right? Right. So, there are a million lines, go here, pick up, drop, go here, pick up, drop, go here, pick up, drop. A million times you write, a million times. That is a very bad way of writing. Okay. A better way of writing would be, if we can have a sub program which will actually do the indexing there, and then the main program will essentially refer to the sub program whenever it has to index. So, the latest way of writing of robot programs is that there are different sub programs for indexing. Say, for indexing there will be one sub program, for spot welding one sub program, spray painting one sub program. So, whenever the main program wants to refer to something, it will just call that sub program, okay, and then perform the task and come back to the main program. Okay. So, that is the way of writing. So, we should not try to write a program line by line and try and go that way. It is a very bad way. Okay. So, how is this one written? First, we see that there are 1, 2, 3 rows and 4 columns. Okay, 3 rows, 4 columns. Okay, and this is the top. This is the layout, the coordinates. So, the way this program is written is essentially we know the coordinates of that point corner. This is the coordinate of the point. We know the coordinate. Then we shift the coordinate by 20 millimeters here, 20 millimeters there, and bring it here. Okay. Then what the indexing fellow does, the subprogram, it just indexes and takes it there, 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 then takes it there, there, there. So, the main program will simply move it to here, pick up, drop, index it, then come back to the main program, pick up this guy, drop it there. Okay. That is what is done. So, the program that is written is here. It is very simple. So, first you fix the constants. So, maximum row is 4 and maximum column is 4 and maximum row is 3. Okay. So, if I want to change the indexing setup now, I can simply change that number and everything changes. Okay. I do not have to write the program again. Second is start row 1, start column 1. Okay. Then the coordinate of the corner point, corner is known. So, I assign a variable pick to be equal to corner. Okay. So, I have set the number of rows, I have set the number of columns. I have started off by 1, 1, saying that I am going to start with the first one now, and I am going to know the coordinate of, I am putting the variable name pick equal to the corner coordinates, which is known. Okay. Then what we do, we shift pick by 20 minus 20, 60. Okay. So, what was done, this was the corner point, we are shifting pick by 20 minus 20 and 60 on top of the object. Okay. So, I am shifting the corner point to the top of this one. Okay. Then what we are doing is, we are saying open eye. So, it is open eye. Okay. So, it is open the gripper, then move to the pick point, okay, which is on top of the object. Then you draw. So, we could use approach here or draw by 0, 0, minus 25, then close. Okay. Then after close, we again draw, we go backward, and then we move to the point, drop point. Okay. So, this is my z axis, this is 0, 0, 0. So, here this side is positive, this side is negative. Okay. So, when we are saying move minus, it is going down, we are saying move plus, it is going up, okay, in the z direction. So, we pick up this, drop it there. Okay. So, close eye, draw, it moves up, then move to the cute point, open eye, it drops it, then it goes to the sub program palette. Okay, so this is my subprogram palette. What the subprogram does is indexes the column by 1, okay, and changes that pick point again and checks if the column has exceeded the maximum number of columns. Okay, so it checks, indexes 1 and then checks if it has exceeded the maximum. So if it has exceeded the maximum, it goes to indexes the row now. Okay, so it was on top here, so it goes from here, 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 plus 1, it goes here, plus 1 here, plus 1 here. If it exceeds that 4 number, it goes here, it indexes the row now. Okay, so it goes here if column is greater than this 20, otherwise shift pick by 50. So which basically means that shifted by 50, 50 is this side, so it comes here. Okay, so we are basically indexing it. Okay, so this point is being shifted here, 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 then it's shifted here, 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 like this in that order. The moment we exceed everything, so if the row is exceeding the maximum number of rows, then go 30. Okay, so 30 is return, it comes back to this line and then goes to end. Okay, so it ends the program. Okay, now if I change this number, the same program will run for any indexing. Okay, so the idea of writing programs today is by making very, very small subprograms which you can integrate and just call whenever you like. So the same robot can do different at different times without changing the main program. Okay, and the language is very, very simple. I think anybody can write, but you have to be a little careful. Okay, so in the lab we'll be seeing the Puma robot is there, and it is also programmed using Val language. So when you go to the lab, you'll be looking at how the program is done using Val. Okay, Val 2. Okay, so today I think it's 5:30 and it's enough for the first day. Okay, so we stop today here and then we'll see you again tomorrow morning. Okay, okay, let's stop today.